Welcome to the Chemistry, Biology and Math Revision Hub. Today we're diving into A-Level Chemistry on Kinetics, part of the Pearson Edexcel International A-Level syllabus. Let's begin with the first part. We're going to begin by looking at methods for measuring the rate of a reaction. The rate of a reaction measures how fast reactants are converted into products, and the rate is equal to concentration divided by the time. This is the experimental time. The units are going to be mole per decimeter cubed per second. So among the methods used, we'll begin with mass change. This change in mass is usually used when there is a gas produced, like we see here. The reactants are placed in a reaction flask and placed on a balance. And then as the reaction progresses, a gas is produced. The gas is going to get out because the cotton wool cannot prevent the gas from escaping. It will escape. And as it goes away, the mass is going to decrease. So the progress of reaction is going to be determined, or is going to be known by seeing how much the mass is decreasing. And this mass is going to be recorded over time, and a graph of mass over time is going to be drawn, and it's going to be used to calculate the rate. We could also use volume of gas evolved. Again, in experiments where gas is evolved, we can collect it using two methods. We could collect it using a syringe, or we can collect using an inverted measuring cylinder. Both methods work, but this one here is more useful when the gas volume produced is less. This one can be used when there is much volume of gas produced. The reason for that is because some gas is going to dissolve in the water, and that could interfere with the experimental results. So you want to use that when there is much volume of gas produced. Otherwise, this one here is going to be more accurate using a syringe to collect the gas. So then we're going to draw a graph of volume versus time, and then we can use that to be able to calculate the rate of reaction at a specific time. Moving on to colorimetry. This is going to be effective if we have colored species. We will use a calibration curve. So basically we'll calibrate and then get the absorbance. This should be absorbance. We get the absorbance that corresponds to a specific concentration, and then we can be able to plot a concentration versus time curve. We will get the absorbance, but remember we already have a calibration curve that is going to be used to get the corresponding concentration. We're going to see how the concentration changes over time, and then we can be able to determine the rate of reaction at a specific time. An example of a reaction that can be followed using colorimetry is the iodination of propanol. We'll look at this a little bit later. The brown color is going to decrease, or the color becomes colorless as iodine is used up during the experiment. During titration, as we can see the setup here, as the experiment reacts, let's say this is the experimental flask where the reaction is taking place, we will periodically take off small samples at regular intervals. Let's say this is going to be 2 minutes, then at 4 minutes as the reaction progresses. Those aliquots are going to be quenched at first. We could quench using an ice bath, or we could use another reagent. Sometimes they use sodium hydrogen carbonate if there is an acid that needs to be removed in order to start the reaction. Meaning, even if we leave the aliquots to settle down, they will not continue reacting. And so any concentration of ions or any concentration of particles are going to remain the same until we can titrate. To determine the concentration, you'll titrate with a known solution, and then or solution whose concentration is known, in order to find out the concentration of maybe reactant or product within the aliquots that were taken off. Then you draw a concentration time graph in order to determine the rate at a specific time. So in this example here, we have propanol reacting with iodine. Like we said already, due to iodine, this is going to be brown, and the color is going to decrease slowly or disappear as the colored iodine is used up to become iodide. However, as this reaction progresses, we are going to be watching iodine because it's going to be used in this titration reaction. So we will take off aliquots like I've already described here, take off aliquots periodically, and you titrate with thiosulfate here, because the iodine reactant will still be there as the reaction progresses. Of course, the concentration of iodine is going to decrease as the reaction progresses, so titrating with thiosulfate enables us to know the concentration of iodine in the reaction mixture. So we can draw a concentration versus time curve in order to see, or in order to calculate the rate of a reaction. We could do electrical conductivity. This is very useful if there is a change in the total number of ions in solution during a reaction. The change in conductivity is going to be measured using a conductivity meter. An example is bromide reacting with bromate 5 in acidic conditions to give us bromine and water. As this reaction progresses, there is going to be a change in the total number of ions, and so we can use a conductivity meter in order to know the electrical conductivity, and then we can plot the results on a graph in order to determine the rate. We could also do refractive index, chirality, change in volume, and many more that were not detailedly discussed in your textbook. Next, let's go to rates and the rate equation. The rate of a reaction can tell us how fast reactants are going to be converted into products, but the rate is going to depend on the concentration of reactants as well as the K value. So the formula rate is proportional to the concentration of the reactants is important. And if we use an example of a reaction, let's assume A reacts with B to give us C. For this, the rate equation could be rate equals to K, which is the rate constant, into the concentration of A power M. M is an order with respect to A, and then times the concentration of B power N, where N is the order with respect to B. I've already stated M and N are orders of reactants with respect to each species. Orders can be 0, first, or second. These are orders with respect to reactant species, and the total order will be the sum of M plus N, in this case here, if we are referring to that rate equation. So when we look at the rate constant, of course, it's going to be affected by temperature. It is going to be constant when temperature is constant, but when temperature changes, it also changes. The units for the rate constant are going to depend on the reaction orders, like we're going to see here. So looking at the units for the rate constant, it depends. Remember, rate equals to K into concentration of reactants. Let's assume like that. So meaning K should equal to the rate, which is mole per decimeter cubed per second, divide by the two are going to be mole, let's assume first order, mole squared, and per decimeter power 6. We can work out the units of K. So an example for a zero order reaction, the units for K are going to be mole per decimeter cubed per second, because rate for zero order rate is proportional to K, and since the units for rate are mole per decimeter cubed per second, they're going to have the same units. For first order, it's going to be per second. Again, for that, you can see K should be the rate, which is mole per decimeter cubed per second. Now per second, divide by, in this case, if it's first order, it's going to be just mole per decimeter cubed. So this leaves us with per second as the left unit. And then for second order, it's going to be decimeter cubed per mole per second. And for third order, it's going to be decimeter power 6 per mole squared per second. These kind of questions are very common in section A, where they ask you to calculate the units for K. So please try to practice. Going on to reaction mechanisms, many reactions are going to be represented in stoichiometric equations. However, these do not show how the actual mechanism is going to take place. Mechanisms are sequences of steps by which reactants are converted into products. Using this as an example, the reactants cannot tell the whole story of how the mechanism is going to go. If we look at the reaction, we have 5 ions and then manganate is 1, so they are not representative. This suggests that it's not a single step mechanism. When we look at this, we can confirm that until the rate determining step, only 1 manganate ion and 2 iron-2 ions were able to react, and that's why they appear in the rate equation, yet other components do not appear. So this is not a single step mechanism. It involves multiple step mechanisms, and the slowest step is going to be the rate determining step, in which these have already reacted, or they react until the rate determining step. Going to the rate determining step, this is the slowest step of a reaction mechanism. It includes all species that have reacted before and in the rate determining step, and the powers of the rate equation are going to be the number of molecules that have been until, or that have reacted until the rate determining step. Let's look at an example where nitrogen monoxide and hydrogen react to form nitrogen and water. In this reaction, they've given us also the mechanism here. So since this is the slowest step, we assume we're going to use the particles until this step here. So this is the rate determining step, meaning 2 NOs, and these ones cancel with that because they're just part of the intermediate, not part of the reactant. So it's only 2 nitrogen monoxides and 1 hydrogen that have reacted until the rate determining step, meaning the rate equation should be rate equals to K into the concentration of NO power 2. These coefficients are going to be the orders with respect to the reactants. Hydrogen is 1, so the order is going to be 1 with respect to hydrogen. And so this is going to be the overall rate equation for that specific reaction. So we're going to move on to determining the orders with respect to reactants. We will use two methods. The first one, we're going to use the continuous method. In this continuous method, the experiment is going to take place, and then aliquots are going to be taken off periodically. Of course, the time at which they're taken off is going to be noted, and the concentration is going to be determined either by titration or another appropriate method. Then we'll plot a concentration time graph. After, we will look at the concentration time graph in order to determine the rate with respect to a specific reactant. So if it's zero order, rate is equal to K. In this case, we can see the concentration time graph is going to be like that. It's going to be a straight line that shows a linear decrease. And then when we go to first order, of course, rate is equal to K into concentration of the reactant. That is going to be studied. The concentration time curve is an exponential decay with constant half-life. If you double the concentration of A, the rate is also going to double because the rate equation is like that. When we go to second order, here rate is equal to K into the concentration of A squared. If you look at the concentration time graph, this is an exponential decay as well, but it's steeper in comparison to the first order one. And so, because this is second order, when you double the concentration of A, the rate is going to be increased by a factor of 4. To show that by calculation, let's say rate will equal to K into twice the concentration of A, meaning K into 4 times A. We can see it's going to be 4K concentration of A, meaning the rate has increased by a factor of 4 in comparison to the initial one when the concentration of A was not doubled. Going on to calculating rate from a graph. Usually if you're given a graph, it could be a curve. If it's a curve, using this as an example, this is a curve of concentration versus time. To determine the rate, we'll draw a tangent at a specific time during the reaction and then calculate the gradient of that tangent. An example, this is extracted from your textbook. A tangent was drawn at a specific point here, and then the gradient of that was determined. Here they used the x value 1470 and the y value that, and then the point here. So they used these 2 points, and then they determined rate is equal to change in concentration of the reactants divided by time. So this is going to be change in the y value divided by the change in the x value, and then they got 1.09 times 10 power negative 3 mole per decimeter cube per second as the gradient. Also, if you have a volume of gas evolved versus time and a curve is drawn in this manner, we can draw a tangent at a specific time and use that tangent to calculate the rate at that particular time. This question is very common in Unit 4, where they give you data, they ask you to draw a graph, and then they ask you to find the specific rate of reaction. Then we can go to the initial rate method. This is a method of determining order with respect to a certain reactant. In this reaction, we're going to use several reaction mixtures by varying the concentration of the initial reactant and then observe how that affects the initial rate. And then we'll calculate a mathematical relationship between the rate of reaction and the concentration. So if there is an example, assume you're doubling the concentration. If it's zero order, doubling the concentration will have no change. If it's first order, we've already seen when you double the concentration, the rate doubles. And if it's second order, you double, the rate is multiplied by a factor of 4. So this is a good example. An example that can come usually in section B or could be section C of Unit 4. Assume you're given this question, a reaction between reactants A and B were studied, the following rate data were collected. So they want you to determine the order of reaction with respect to A and B, and then write the rate equation for this reaction, explain your reasoning. So I will begin by looking at experiment 1 and 2 because we see this concentration is constant while this one here is doubled. So you can say doubling the concentration while keeping this constant. You can see there is a doubling in the rate. The rate moves from this value here to that value, meaning it's first order with respect to A, since as the concentration of A doubled, the rate also doubled. Then we go to another. We can go to this and that, where these are kept constant, but this one here is doubled. I'm looking at experiment 1 and 3. We can observe the rate does not change. That means it's zero order with respect to B. So let's look at our solution here. I've already explained this. We see it's first order with respect to A because doubling the concentration of A, the rate also doubled. So first order with respect to A, and then for B, we saw if B was doubled, the initial rate had no effect, so it's zero order with respect to B. So the rate equation is going to be K into the concentration of A times B power 0, which is basically rate equals to K into the concentration of A as the answer. So we've written our rate equation and our explanation is included here. Finally, you could say the order with respect to A is first order because doubling A doubles the rate. This is the conclusion for the final solution, but I've already also explained it here, even if you do not write. Then the order with respect to B is zero order because doubling B has no effect on rate. And this is going to be the final rate equation. Next, we'll move on to orders from a rate concentration graph. A rate concentration graph can also be used to observe or to know the orders with respect to a specific reactant. Let's take an example for zero order. When you draw a graph of rate versus concentration, it's going to be a flat or horizontal line like we see here. So in an experiment, if you're given results and you draw a graph of rate versus concentration, if it comes out as a horizontal line, then that is zero order with respect to that reactant. For first order, it's a straight line through the origin. And then for second order, it's going to be a quadratic graph like we see here. Next, we'll move on to elementary reactions. Like we said, elementary reactions or an elementary reaction is a single step in a reaction mechanism that happens exactly as it's written. The stoichiometric coefficients of this elementary reaction are going to equal to the number of particles that are colliding in that specific reaction. So an example, if you have a reaction A plus B gives us C, this means 1A particle. Because the coefficient here is 1 and this coefficient is 1, so 1A particle collides with 1B particle in that specific reaction. Let's take an example. If A reacts to give us products, because one reactant is reacting, it means the order with respect to A is going to be 1, since it reacts in a single collision. If A reacts with B to give us C, and again, these are all elementary reactions, rate is going to be bimolecular because two molecules are reacting. However, the rate will equal to K into 1A reacted and 1B. So it's going to be concentration of A power 1 times the concentration of B power 1, since the coefficients in the reactions were both 1 and 1. So it's going to be first order with respect to A and first order with respect to B. Then consider a third situation where 1A reacts with 1A to give us the products. Still two molecules are reacting, so it's going to be bimolecular. However, the rate equation is going to be K into the concentration of A squared, since two of these are reacting and they're the same. So it's going to be second order with respect to A and is second order overall. Then reaction mechanisms. Of course, reaction mechanisms are going to be sequences of elementary reactions like we've already seen. The overall equation may hide those multi-steps, and the rate determining step is going to be the slowest step. Elementary reactions, like we said already, they're single collisions whereby reactants are converted into products in one step, and they follow the stoichiometry of the equation. Taking an example, 1NO reacts with 1 ozone, meaning if this is the elementary reaction, the rate equation is going to be rate equals to K into concentration of this power 1 times the concentration of that power 1, because the whole reaction is elementary. Now, there are some reactions that are non-elementary, meaning they take place in multiple steps, not elementary like this one, which is a single step reaction. In these multiple step reactions, it means they have multiple elementary reactions. So in multiple steps, the intermediates are not in the overall reaction like we're going to see here. An example, if N2O5, two of them react to give us NO2 and then oxygen, you would expect the rate to equal to K into the concentration of N2O5 squared. But actually the rate equation is this: rate is equal to K into the concentration of N2O5, meaning this is wrong, and therefore this is not a single step collision. It occurs in two steps, whereby from the beginning until the rate determining step, it's only one N2O5 that has reacted, and so this appears in the rate equation. Going on to examples of multi-step reactions, consider methane reacting with chlorine to give us chloromethane and hydrogen chloride. In the first step, chlorine is going to give us two chlorine free radicals in a fast step, And then the chlorine radical reacts with the methane to give us HCl and the methyl radical. This is the slow step, and so is the rate determining step. We'll consider these two steps when we are writing the rate equation. So it's going to be only chlorine and the CH4 that show up in the rate equation. Even though after the slow step, the methyl radical reacts with chlorine to give us the final products in a faster step, this does not appear in the rate equation. So the intermediates, which are this one and this one here, did not appear in the rate equation, as we can see here. So we've only considered the particles that reacted until the rate determining step. Those appear in the rate equation. Let's move on to halogenoalkanes. We're going to be focusing on the mechanisms SN1 and SN2. SN1 stands for substitution nucleophilic unimolecular, meaning one molecule is taking part until the rate determining step. This is going to be a two-mechanism reaction since only one molecule takes place until the rate determining step. It means the other molecule reacts after the rate determining step. The halogenoalkane is converted into a carbocation intermediate, and then in the next step, the nucleophile is going to attack. So since only the halogenoalkane was present until the rate determining step, or in the rate determining step, rate is going to be proportional to the concentration of the halogenoalkane only. So only this is going to appear, its concentration will appear in the rate equation. And for this reaction here, the rate equation is going to be rate equals to K into the concentration of this halogenoalkane only. So when we look at the graph that is going to result, we can see the halogenoalkane reacting with a hydroxide, but because this is a two-step reaction, the first one is going to be leading to the formation of the intermediate, which is the carbocation. We see the activation energy for this is actually bigger than that for the second in order for us to get the products. But the intermediate is a little bit more stable, so the reaction can proceed. For tertiary halogenoalkanes, they prefer to proceed through SN1 mechanism. Moving on to substitution nucleophilic bimolecular SN2. This is a single-step mechanism in which the nucleophile is going to attack as one is leaving, creating a transition state. And if you're writing the rate equation, it's going to be rate is proportional to the concentration of the halogenoalkane times the concentration of the nucleophile. Since this is going to be 1, it's an elementary step, so power 1, so the orders are going to be 1 with respect to each. An example is this halogenoalkane reacting with hydroxide to give us that. The rate law will be rate equals to K into the concentration of this times the concentration of that, as you see there. And looking at the graph for SN2, we can see the reactants react in a single step, and then they're going to be converted into products, as we see there. To conclude this, SN1 is preferable for tertiary halogenoalkanes, and SN2 is preferable for primary halogenoalkanes. I will focus on this a little bit later to explain it a little bit more. A good example is iodination of propanol. This is called practical 9A. There is a reaction taking place between iodine, propanol, and acidified, of course, so there is some acid giving us these products here. The strategy here is to use excess propanol and excess acid. So if this is excess and this is excess, it means we can study how changing the concentration of this affects the rate of reaction. So the procedure is you could mix 25 centimeters cubed of propanol with 25 centimeters cubed of the acid, both 1 mole per decimeter cubed, and then you add 50 centimeters cubed of iodine, 0.02 mole per decimeter cubed, and you start the timer immediately. So as the reaction progresses, you're going to quench 10 centimeters cubed samples. At regular intervals, this could be 5 minutes. You're going to take them off periodically and quench. Then you titrate the remaining iodine in the reaction mixture with sodium thiosulfate. We saw the equation for this reaction before using starch indicator. And then you can be able to determine the concentration of iodine left in there. Then you plot the graph of the concentration of iodine versus time to find the order with respect to iodine. You could do this with other reactants. For example, you could give excess iodine, excess hydrogen ions to determine the order with respect to propanol, and then later you can make propanol excess and iodine excess and determine the order with respect to H+. So you'll find that is zero order with iodine, first order in propanol, and first order in the acid. You're not required to know this. In the exam, they will help you to calculate. They'll give you some data that can help you get it. And the rate law is going to equal to rate equals to K into the concentration of propanol times the concentration of the acid. Next, we go to activation energy and catalysis. We know a catalyst creates a new pathway with lower activation energy. And this activation energy is the minimum amount of energy that colliding particles must possess in order for reactants to be converted into products. As the reaction proceeds, the reactants have to go through a transition state, meaning they need to gain energy. This is going to be endothermic. And after they gain the transition state, they will release energy as they form products. The catalysts used can be homogeneous or they can be heterogeneous. Let's look at homogeneous catalysts. The example, iodination of propanol. You remember we used acid as the catalyst. In this reaction, this is aqueous, and then we can see aqueous. Everything else is aqueous, including the catalyst. So that reaction is homogeneous, or I would say the catalyst used there is homogeneous since they are all in the same state. When we go to the CFCs or chlorofluorocarbons reacting with ozone, they produce chlorine free radicals in the presence of UV. Here, the chlorine radicals are going to be the catalysts for this reaction. And since everything is in gaseous state, we can see there, this is going to be the gaseous catalyst. So this is still homogeneous. And the overall reaction here is going to be 2 ozones, the gas gave us, 3 oxygens, which are gas as well. In this reaction, because both reactants are negatively charged, they will repel each other, and so the rate of reaction is going to be slowed down. So using a positive catalyst, which could either be iron 2 plus or iron 3 plus, is going to be helpful. Now in this example here, iron 2 plus is used as a catalyst, and it will react with peroxide sulfate first in order to give us sulfate and iron 3, and then this iron 3 is going to be reduced back to iron 2 as iodide reacts with it to give us iodine. This is a 2-step reaction when peroxide sulfate reacts with iodide ions, and the catalyst is going to be regenerated. Next, we move on to heterogeneous catalysts. Usually here the catalyst is going to be a solid. The example we have is the Haber process in making ammonia. Nitrogen gas reacts with hydrogen gas to give us ammonia gas, but here we use iron as a catalyst. This is iron metal. It's not Fe2 plus or Fe3, it's just Fe, the metal itself. Of course, hydrogen is going to adsorb onto the surface of iron, forming interstitial hydrides. The activation energy for the reaction is going to be decreased, or the new pathway with low activation energy, and then the reactants are going to react on the surface of the catalyst, and after the products are going to dissolve off the surface of the catalyst. Problems about using some of these catalysts is that they can be poisoned by impurities. For example, nickel can be used instead of platinum because it's cheaper and effective, but can be poisoned, and that could lead to problems, although it's cheaper. Some scientists overcome this by using promoters to improve the catalyst efficiency. For example, iron in the Haber process is promoted using potassium oxide or aluminum oxide. Moving on to the 3-way catalytic converter. This is usually placed in car engines or at the exhaust part of the car engines. This is used to convert the harmful exhaust gases into safer ones. For example, in converting unburned hydrocarbons into carbon dioxide and water. Also, it can be used to convert carbon monoxide into carbon dioxide, and then converting oxides of nitrogen into nitrogen as well as oxygen. Let's move on to autocatalysis. In a reaction where ethane dioic acid reacts with manganate 7, in acidic conditions, because it's acidified, we produce carbon dioxide, manganese 2, and water. In this case, this is going to be the catalyst. We call it an autocatalyst because the reaction is self-catalyzing. Initially, when we look at the concentration time graph, we're looking at the concentration of the reactant. It takes longer to decrease. Initially, we can see the reaction starts off slowly because there is no catalyst. And more so, if it's at room temperature, the reaction is going to be even slower. So some people could heat the reactants in order to speed up a little bit so that Mn2 plus forms faster. So this slow reaction then begins to proceed. We see the faster rate of reaction occurring as more of the Mn2 plus is formed that catalyzes the reaction, and in the end the reaction is going to slow down and eventually come to a stop when all the reactants are used up. Please remember this graph and remember how to describe it, because the graph itself can come in either section A, section B, and they could ask questions about it. So do not forget that. Arrhenius equation, this part is very common in the exam. Here we use the equation natural log of K is equal to natural log of A minus EA over RT. It follows y equals mx plus c. I can rewrite it in that manner. Natural log of K is equal to negative EA over RT plus natural log of A. When you draw the graph, this is the y-intercept corresponding to C, the value here where the line drawn touches the y-axis. And then this is going to be the value on the y-axis, you see natural log of K. Then the value on the x-axis is going to be 1 over t, this part. So the gradient is going to be negative EA over R, because m is the gradient, x is the x-axis value, y is natural log of K on the y value, and then natural log of A is the constant, which is the y-intercept. So the remaining part is negative EA over R, which is the gradient. So here we use an example from your textbook. They say use the table below to draw a graph of natural log of K versus 1 over T. Use the graph to find the activation energy. The data is given. Sometimes they just give you the value for temperature and then the value for K here. And you will be required to draw more columns in order to create the value for natural log of K and the value for 1 over T, since these are the values you're going to use in order to draw your graph. This goes to the y-axis and this goes to the x-axis. And then you plot the points like we see here and draw a suitable line through the points. And finally, you find the gradient of that line. To find the gradient of the line, find 2 accurate points into which the line of best fit crosses. So in this example, they found this value here, that value for y, and then the x value, that and that. And they were used in order to calculate the gradient, which is negative EA over R. Using the calculator, this is the value for gradient they got. But remember that R value is 8.31 joule per mole per Kelvin. So activation energy was the negative of this value, which becomes 4538 times 8.31, giving us the final answer, which is later converted to kilojoules per mole. That is going to be the activation energy. Please do not forget to put the sign. It's very important that you put it there. The part I'm explaining here is in part of Did You Know, but I think it's important. I'm explaining halogenoalkanes and the mechanisms, why tertiary halogenoalkanes prefer to go through SN1 and why primary halogenoalkanes prefer to go through SN2. We're going to look at 2 factors. One is inductive effect and the other is steric hindrance. Inductive effect is when there are more groups that are electron donating. For example, if we look at primary halogenoalkanes, they only have 1 R group, which is electron donating. Secondary halogenoalkanes have 2 electron donating R groups. The hydrogen is not electron donating. And tertiary have 3 electron donating groups, meaning if they were to form a carbocation, this is going to be more stable in comparison to primary and secondary. And if a stable carbocation intermediate is formed, it means the activation energy for that reaction is going to be lower, and so reactants will prefer to go through that pathway. So stability of carbocations is going to be tertiary, more stable than secondary, which is more stable than primary. And like I said already, a more stable carbocation means lower EA for the reaction, meaning that reaction will proceed faster. Then there is another factor called steric hindrance. Steric hindrance is if you're reacting to groups, let's say Rx, the halogenoalkane, plus OH. If there are so many R groups, let's say R3X, like in tertiary, they are blocking the place where this other OH should come. Maybe I should draw this. We have carbon, there is R1, there is R2, and there is R3. Then there is your halogen, let's call it X, and the nucleophile is incoming. In this case, if the nucleophile comes in, we will have 5 groups. If it's to go through a transition state, the 5 groups in a transition state will be too much. And in this case, it's going to be blocking or the blockage. And again, if you see some of these R groups are going to be carbon, hydrogen, hydrogen, and hydrogen. If I display them more, then it's more hindering or it's showing more hindrance. So the nucleophile will have no space for it to attack. And as a result, the nucleophile waits for this to leave, creating the space in an SN1 mechanism so that the nucleophile can attack later in the next step. So these two factors, inductive effect and steric hindrance, are the reason why tertiary halogenoalkanes go through SN1, and the primary halogenoalkanes prefer to go through SN2. Why? There is less steric hindrance, and there is no inductive effect to lead to a lowering of the activation energy. So to tertiary, SN1 is favorable, and to the primary, SN2 is favorable. There are things they love in exams. Please remember identifying orders from graphs. Could be concentration time or rate concentration graphs. There is also another I didn't talk about. There is rate versus concentration squared. Concentration squared. Usually this is for second order. This is going to be a straight line through the origin as well, similar to what we would see in a rate concentration graph for first order, but this is for second order, and the x-axis is concentration squared, not just concentration. So they could bring concentration time graphs or rate concentration graphs and ask you to determine the order. Using initial rates to determine the orders with respect to reactants, as well as writing the rate equation. They can ask you to sketch and interpret Arrhenius graphs, as well as calculating the activation energy, describing experimental methods for finding the rates, sometimes colorimetry or the gas volume. And for the gas volume, they can ask you why you use a syringe or why you use an inverted measuring cylinder, so you need to know that. They can ask you to explain how heterogeneous catalysts work, remember the adsorption mechanism, and then finally, mechanisms of SN1 and SN2, when each happens and why. Remember, we have said SN1 usually in tertiary and SN2 usually in primary. The exam tips: please remember to use the units of K correctly. They love asking about that. And then label your graph axis clearly when you're drawing. The initial rate of variation is determined by drawing a tangent at time equals to 0. And then the Arrhenius graph, you remember it has a negative gradient. And of course, a catalyst creates a new pathway with low activation energy. If I'm to add on something, they like asking natural log of K equals negative EA over RT plus natural log of A. In this, I have seen various scenarios where they give you the tables or the table with results of maybe natural log of K at two different temperatures. So you have temperature 1 and temperature 2, and the corresponding natural log of Ks. And then they ask you to find maybe the activation energy. If this is given and this is known, we will be able to use something like a simultaneous equation. Since this is a constant, it's going to be cancelled out. So natural log of K1 equals negative EA over R T1 plus natural log of A. And then natural log of K2 equals negative EA over R T2 plus natural log of A. And then we combine them by elimination. So subtract. This is going to be natural log of K1 minus natural log of K2 equals negative EA over R into 1 over T1 minus 1 over T2. Because the A cancels out, if you subtract them, they disappear. So here, to simplify, if you're subtracting two logs, it's going to be the same as natural log of K1 divided by K2 equals negative EA over R into 1 over T1 minus 1 over T2. So in this case, we have K1 and K2. Just use your calculator to find that. We have the temperatures. Use your calculator to find that. And then we know this, so we can be able to find the activation energy using that information. Please remember this. It comes quite a bit, and some students may not remember because it's not in the textbook, meaning this kind of example is not in your textbook. So please remember that. So I've included a slide on classic traps they love. Confusing zero order with first order. Please remember to look at those graphs and their shapes. Forgetting SN1, rate depends only on the halogenoalkane. Writing EA increases for a catalyst, which is wrong, it decreases. And missing the rate determining step. Please remember to link to the rate equation. And assuming Arrhenius plot is linear forever. Please remember it has some limits. So this brings us to the end of this lesson on kinetics. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.